João is working in a lab in the University of Porto that is related to artificial intelligence and decision aid, and in the Faculty of Engineering. So he is going to present his research group, the different projects he has been working on, and what are the main research interests. Also some doctoral students research projects that they have running right now, in order that later we can see potential collaborations in terms of potential future projects, but also maybe research visits, some student that could come from Porto, or some student from here who could go also to Porto. Let's see what are the different ways that we can explore to go further with this collaboration. So thanks for coming, for your interest to be here with us. And now the floor is yours, and you can begin with the presentation.
Okay, can you hear me well? Okay. I have divided this presentation in three components. One is presentation of INESCTEC, that is the research unit I belong to give an idea of what it is. Then I will talk about three PhD works I have on the area of explainability. And in third, I will talk about what we think it is, a new paradigm of machine learning, that we name it rewrite machine learning, that was the result of a PhD student that defended his thesis in May 29th, quite recently. So I will work on this. So firstly, INESCTEC is a research unit, is a research lab that is a private institution without, let's say, non-profit research unit. Is located in Porto, but has connections with other cities that I will show later. In fact, it is connected with three main universities of north of Portugal: University of Porto, Universidade do Minho, University of Trás-Montes e Alto Douro, and also ISEP, that is the Polytechnic Institute. It is a large, let's say, center. It has 13 centers of research in different areas. I will talk a bit about that. And also as, let's say, this is divided in 8, I think, research lines, and also in what we call Tech 4 initiatives. What are these Tech 4 initiatives? Are, let's say, lines that are of budget interest, of market interest. Okay, I will talk a bit more next. In terms of research, the research lines we have are the INESCTEC is artificial intelligence, bioengineering, communications, computer science and engineering, photonics, power and energy systems is quite strong in that topic. It was the first one. Robotics, we have also quite good team in robotics, and systems engineering and management. In terms of the Tech 4 initiatives for more directed to the market are the R5, that is Tech 4 agro-food, Tech 4 energy, Tech 4 health, Tech 4 industry, and Tech 4 C. Basically, these initiatives use the resources of all centers according to their what is needed for a given, let's say, project or initiative. In terms of budget and technology readiness, you can see more or less here how it is, let's say, from the knowledge production to transfer, how the different fundings, namely national fundings, European fundings, and other ways of funding are applied along technology readiness levels. For instance, the first knowledge production are more based on national and European projects, while, for instance, R&D and national competitive fundings are more on development and transfer area. In terms, nowadays, the research lines has changed. We changed a bit how we organize themselves, and nowadays, since 2022, we are organized in 8 lines, as I have told before. In terms of numbers, we have 183 faculty members, 213 employees in general, and 223 PhD students and 11 postdocs. These are numbers of 2023, 1 year ago, but I think it didn't change too much. This is our production. You can get an idea of our production in terms of publications. For instance, in 2022 we have published 465 journal papers, or 379 conference papers. Well, let's say is a reasonably large research center. Now I will show you the collaborations we have. We have collaborations with several countries. The main is United States, because it's a strong economy, but in second place it appears Spain, because it's our neighbor. And Brazil also is important for us, because strong connections due to the language and historic connections. But we have connections with many different countries: Germany, Italy, France, etc. In terms of funding, you can see especially the plot on the left, that is let's say national fundings and European fundings are the ones that bring more money to the institution. These are some areas that where we did some things that had some impact. Namely, there is one that has 3 million downloads. That was Stay Away COVID. That was an application to see if someone nearby was with COVID, so we could move away if we want. But there are other in many different areas, in the area of energy, and also in for forest fires. There were applications, and also for health we have many things done on these areas. Now I will talk a bit more in detail about one of the 13 centers. That is LIAD. LIAD means Lab in Artificial Intelligence and Decision Support. We are 24 faculty members and 30 students, typically PhD students. And our areas of interest are on, I will talk only on the component of machine learning, but we also have a group that works on mathematical modeling. On machine learning, let's say, algorithms, obviously, data streams. João is, let's say, the top researcher on this topic. In temporal and spatio-temporal learning, me personally, I work a lot on this topic. In mining extreme values and predictive maintenance, this is a work that is being mainly Rita Ribeiro and Luís Torgo, but Luís Torgo unhappily decided quite recently that to work on this area. And in recommender systems and NLP, this is a work of Alípio Jorge, and Carlos Soares also work a lot on recommender systems. And in AutoML and meta learning is a work on Pavel Brasil that is retired but still continue to do research, and Carlos Soares that work a lot on these topics. Well, my research is presented here in a very summarized way. Each rectangle is a PhD student. The ones with shaded ends means that they have already finished PhD. The blue ovals are research areas, and the green ones are application areas, let's say. So I will talk today about what I have on explainability. That you can see that on explainability I have 3 students. It is Tiago Mendes, Pedro Streste and Ahmed Farj working on it. And also I will work on read and write machine learning. That was a work of Yassin that defended the thesis recently.
How do you apply deep learning to football, I wonder?
This is a quite interesting work done by Tiago Neves. Tiago Neves, what he did was to create a large event model that is able to simulate a soccer game. For instance, basically he predicts the next event, and from next event he predicts the following one, and so on. Okay, and with this he can do a lot of applications quite peculiar. For instance,
like application like gambling, no?
No, but for instance, you can test how a different player could behave in a different team. If you put that player in a different team, you could see if it could be a good contribution or not, things like that. It gives a simulator, basically a game simulator based on characteristics of each player and of each team. Not, let's say, a generic simulator. Sorry, more questions about this that you would like to ask? In the left are the topics that personally I have more interest on research. Okay. Just concluding, Tiago Neves is nowadays he will finish PhD in 1 year more or less, and he's working in a company that does crowdfunding of young players, young people that want to play football, and is, let's say, is intended to exploit commercially what he did in PhD. He's a very proactive person. Now I will talk about a work by Pedro Strete that expectedly will finish the PhD in 1 year, more or less. He's already writing the thesis. And this is some connection to explainability that I will explain afterwards. Let's say, imagine that you have, let's say, a model for, I will give a practical example. The university is organized in faculties. The faculties are organized in departments. Departments can have different programs, and each program has different curricular units. The way to change a curricular unit, you need your let's say, your active thing is the curricular unit itself. If you want that the director of the program see the curricular units that they have in his program, you will have around, I don't know, 30, 40 curricular units to observe. The director of the faculty will have hundreds, and the director will have thousands. In the University of Porto, it will be 5,000 something. So our idea is, why not? We want to keep curricular unit as the unit of observation, but of course the rectorate doesn't want to see all the curricular units because it's not able to to deal with all that information. So our idea was to cluster the decision trees in order to have a kind of profiles, let's say 7 or 8, so that we can have an idea of types of behavior of the different curricular units. So we aggregate.
It's a course.
Course, like training course.
Yeah, because this Portuguese name for the curricular unit is not very well known here.
A curricular unit
Yeah.
is a course. It's a course. Okay, I will use the course name course.
That's from the appreciation that there was a.
Okay, so imagine for a director of the faculty, you want to have a number of decision trees that can give you an idea of the typical behavior of the curricular units of that faculty. So we cluster the decision trees so that of each course. Sorry.
What is the decision tree for?
The decision tree can be, for instance, to see in a course if the student was well succeeded or unsucceeded, for instance.
So it
Based on
predicts the
characteristics.
scores of this particular student.
Yes, or to see based on some characteristics to see if he is well succeeded or not. For instance, this is an example. Another example could be a company with different, let's say, businesses in different parts of the world, and you want to see how the economical behavior of each one, but you want to see not the global, you want to see, let's say, how each individually works, and to have an idea of the profiles of all the units of your group, for instance. Okay. So what we do is we train, in that example I gave, a model for each course. Okay, and then we stratify, we split the decision trees we obtain according to a given criteria, by faculty or by whatever. Then we combine the models in a way that we get with a reasonable number, in order that it can be observed let's say, the profile of decision trees we get. We can use these models in the end also to do predictions, but it's not the main objective, let's say. So from the model, what we do is to extract rules, and then one by one we combine the rules until we got a final model that is a consensus model. Okay, it can be one, can be several, depends on the number I want to create. And practical example, imagine that I want to see the sales behavior in each world region. We have 6 world regions. So we would merge the decision trees per region, and we would get, let's say, could be like 5 or 6 or 8 decision trees per one specific region that could give me the idea of in that region what is the profile in each region. If we want to have an idea of the sales behavior of all subsidiaries, we would create only a set of decision trees, let's say 6 or 8 or whatever, for the global area. or in a university, we can aggregate according to a program, or according to a faculty, or according to a university. Okay. This can be seen as a way of giving explainability to something, in the sense of putting at a human level of observation the number of decision trees that, depending on the level of aggregation, we can evaluate things. A second example of work on explainability, but that is still in the beginning, so it's a very initial work. Basically, the idea born from work we have done with a company that is monitoring IT. What is that? Is a company that has, for instance, clients, big companies that have many computers, and they monitor how they work, if there are problems on the computers, etc. And the idea is to be able to detect anomalies that can be happening. So let's say, typically each client of that company has several time series. Each time series is about an indicator, for instance, memory consumption, or the CPU consumption, these kind of things. And what we intend is to be able to detect situations that can be problematic, and to be able to rank them according to a given criteria, and the idea is to do that online. Okay. The first work we have done on that was published in a conference, IDEAL conference in 2023, and basically I will not explain this in too much detail, but the idea is each time series we have an algorithm of concept drift detection and also of outlier detection to detect numbers that are out of expected, that can be considered outliers, and then we group this, we see how many time series have this problem at the same time. Okay, and when that happens, we say that this is an event, when there are more than a given predefined number. And then if there are many complex events happening in continuous moments, we define an alarm that is, let's say, in order to avoid to have too much things that in fact is only one. And then we group this in clusters, and basically what we intend is to be able that the clustering is able to detect from these alarms the ones that in fact correspond to outliers. And then we create some metrics we create 4 different type of metrics to rank these events, let's say, to identify which is the cluster of outliers and to rank the events that are in that cluster. Our idea for explainability is, as you know, I don't know if you know, but ILP is inductive logic programming, is a technique based on logic programming that is able to give good explanations, but in terms of it's not very popular because it's computationally very complex and very demanding. We intend to explore ILP approaches that are not very time demanding, that are more light, let's say, and that can be integrated in the online approach. That is the future work that we expect to follow on this topic. A third work that is still more in the beginning, we have nothing published until now, but is a research line that is more connected with explainability. And the idea is very simple. It was based on a work by the group of Peter Flach, that is a researcher from the University of Bristol. And basically the idea is when we give explanations about a prediction or on a prediction, the question is, can we personalize that explanations based on feedback of the user? That is what we intend to explore, and this is our initial framework that we intend to do, that we have a typical model to give predictions, and then we have a model that produces counterfactuals that the idea is that the user can give feedback on it. But this is an intention more than a work done. About explainability works, if you have any question, please let me know. To conclude, I would like to talk about this work that is a topic that I really like. I think it's a quite peculiar paradigm that makes sense for me. That is read and write machine learning. If you see the image on the top, is a typical process in machine learning for predictive learning. You do some kind of data preparation, then you use a model that has some iterations, and finally you evaluate that thing. Of course, you evaluate that in a test set that was separated, that was not used for learning. What we propose is the following. What we notice is that all the algorithms we know read the data only once, and then iterate several times, but the data keeps stable all the time. Our question or our hypothesis was why same in SQ, for those that came from databases, we know that SQL language has the select instruction, but also has the insert, update, and delete. And the question is, why can't we insert, update, or delete instances from the training set in order that to improve the predictions? That is the idea. So the idea is that we don't need to read only once the data. We can read the data, but change the data. Of course, only the training data, not the test data, obviously. But we can change it in order to improve predictions. If you can think on artificial intelligence, for instance, in the backpropagation algorithm, in each iteration of the backpropagation, there is a forward step and there is a backward step. The backward step aims what? To recalculate the weights. My question is, why not to change the input values? Also,
how
if this
from simply augmenting the data, you get initial data, augmented, apply some augmentation, and that's it. What is the difference between this and your idea?
Data augmentation is not done as an iterative process during the iterations of the process, in the learning process. Here, let's say, the change that is done on the data is done during the learning process and in a way to improve the learning process. Okay? I think that makes a difference. So this is then only makes sense for iterative algorithms or algorithms that have an iterative process, naturally. Okay. So I will only talk about one of the components of PhD thesis of that student that was published quite recently in the Neural Computing and Applications journal. And this is, we call it corrector LSTM. We have used long short-term memory algorithm. We have, this work was done for time series. So the question is, how can we detect problems in recurrent neural networks? How can we detect that changing the data we could improve the prediction? And this is long short-term memory. Okay, this is a cell of long short-term memory, and what we did is to keep long short-term memory, but what we did is in the to predict in the hidden cells, based on the values of the hidden cells, the value of the cell state. And if we detect that the prediction is very different from the real value that happened next, let's say, what we do is try to change the data in order to see if that value, we do that by doing some iterations in order to change that value to see if that difference reduces or not. We do it in the sense that it reduces. Okay, that is the objective. So that you can have an idea, the upper plot presents the image of the hidden cell. Okay, and the time series itself is in the bottom. Okay, here is an example where you can see in the upper part in gray is the component of the hidden cell that corresponds to the part in gray in part of time series. Okay, so we look to the information in the hidden cells to predict the value after of the cell. These are the mathematical details. I will not enter in too much detail here. But you can see in the plots, let's say what is changed on the time series. Okay. These were the experiments we have done. We tested our approach CLSTM against the standard LSTM model. We have used same hyperparameters in order to do a fair comparison, naturally. And we obtained these results. We split these results. We tested in many time series, hundreds of time series, 800 or 900 or something like that. And you can see here that, for instance, in terms of LSTM, for instance, for hourly data, wins 405 times, and CLSTM only wins 191. But for other, CLSTM doesn't work well for hourly, neither for yearly data, but works well for daily, weekly, and monthly data. That is, let's say, the conclusions that we got based on the results that you can see. You can also okay. These are the results we have obtained. This is, let's say, an analysis of the behavior, separating the cases where the CLSTM won and the cases where it have lost. And let's say it's of course what is expected is that when it has lost, CLSTM loses always, and when won, it won always. But it's possibility to analyze in a bit more detail. Here are examples on the behavior of the, let's say, our algorithm in the presence of outliers. For instance, you can see on the right side the corrections that are done to the data. For instance, when you detect the outlier after the correction, you see on the right side how data was changed. Can you understand the idea? Imagine the upper two plots. Okay, you see that there is a risk in the middle. Okay, here there is an outlier. Okay, that was detected. Like we changed the data, and the data, the original one and changed one, is shown on the right side. Okay, let's say this is showing how the data was changed when a detection was observed. Okay. These are other examples. For instance, I will explain this for the two on the upper part. Imagine the data, the first plot on the left upper plot. You can see that the correction, the corrected data is only done by CLSTM, obviously, and you can see how the correction was done. Okay, and then you can see the forecasts done by LSTM and the CLSTM on the right side. Okay, so on the CLSTM uses corrected data, while LSTM uses the, let's say, the original data. If you see, for instance, the one on the right side, the above on the right side, this is clear that, let's say, typically CLSTM has more ability to address more rapidly to the outliers that can happen. Okay. These are more examples connected. Let me only see the time. Okay, so I will not spend too much time now. These are a comparison that we have done with our algorithm with Informer, and we obtained quite interesting results on it. And another thing that we were concerned about was, I will pass this, the ability of the algorithm to deal with outliers. There is a data set that is named NAB, that is Numenta Anomaly Benchmark data sets, and we have tested how our algorithm works against, in that case, against LSTM. And typically it works better. You can see details here, I think. No, sorry, I was mixing with another plot. Yes, but it can, let's say, win in 26 times, while LSTM only wins 6 times. In terms of computational time, we can see that, of course, our algorithm spends more time because it's an additional component. And here are the additional time for the different data sets we have used. This is in seconds. Then we have done let me see. Okay. Now we have done a work comparing with a different algorithm that was created by Numenta, that is the hierarchical temporal memory, that is also a deep learning approach. And we have done our experiments against this algorithm. And here you can see that plot shows on the left the true positive outliers that we detected. We have detected in the X dataset 47 outliers out of 361, while, for instance, the HTM model is only able to detect 7, for instance, and we obtained less false positives. In general, it worked better for all the data sets, except for the last one, for tweets. Finally, just a very final work that was published in the IDA conference this year, and basically was an improvement we did to our CLSTM algorithm. Instead, I didn't tell previously, the algorithm that does the predictions of the cell values based on these and cell values was done using SARIMA, that is a known time series algorithm. In this work, we have used a kernel-based, very simple kernel to do that prediction based on moving averages, weighted moving averages. And we obtained the kernel LSTM was able to obtain better results than both CLSTM and LSTM. But there is one thing that is interesting to observe, is that when it fails strongly, but in general it wins more times. Okay. Finally, and as summary, this is a new paradigm of machine learning, that what we claim here and the works we have done, we believe that are very initial works that can be improved, let's say, is why do we only read the data once when we are training an iterative model? Why can't we let's say, change the data in order to improve the predictions? That is the question, and that is what we intend to promote, let's say. Yes, okay, that's it.
So now it's time for questions. If you want to make questions, I have to give you the mic.
May you come back to the slides with the decision trees merging? But we cannot see anything. Wait.
Now goes out from the projector. I don't know why. Maybe it was
because
time
of
out.
that.
Is the battery or no? The battery is fine. Maybe we're going to fall.
This one?
Yeah. So did I get the idea correctly? You, for example, in the case of universities, you have some kind of subunits of the university, and you train decision trees that predict the performance of students in terms of certain course
Yes.
that is taught in this faculty or whatever, right? And then you take several decision trees trained for different courses but related to the same faculty, right? And then you merge them, right?
Yes.
Okay, and first question is that how do you merge the decision trees?
I will try to explain. The way we merge is defined here. Okay, so imagine you have two decision trees. You extract from decision trees the rules because you can do it very easily, and then you use techniques of rule induction to manage. That has some problems. I'd say there are a problem of completeness, for instance. You probably can have some parts of the input space that get empty, but let's say that can lose. In the limit, the aggregation can be difficult to be done. But generally, we can do it reasonably well.
But do you compare the performance of the predictions of individual trees and the combined trees?
This is done. I don't have here the results for it, but that was done. I'm not sure if this was already published. I think it was in a paper we did in a Willy journal. I think so. But we have done that.
But what I'm mostly interested in, as far as I'm also researching the explainability, how do you understand the explainability of the final trees?
The explainability is very simple. Is that imagine the rector of a university. If he has 5,400 decision trees, for more simple they are, he can't manage them because are too much. And the question is, the aggregating decision trees, you are reducing in number and make it in a human understanding level. In a number that humans can understand.
So do you say that, for example, you have a rector and you have who wants to scan, I don't know, the quality of the courses trained in terms of certain faculties
that exist, the general overview.
And but it's still the decision tree can be enormous. Like, do you mean that the rector will have a look at each decision pass of the decision tree, or what?
Typically, per curricular unit, per course is not so big. If it is for full university, yes, it could be very, very large. But for each course, you are not talking about very too large decision trees. Moreover, when you aggregate decision trees, they get a bit simpler. So the resulting merging decision trees are not enormous, not at all.
So the explanation in terms of like certain sample, like certain course, is performed just by visually inspecting the obtained decision trees.
By two things: by the number of decision trees you need to observe, that is much less, let's say, and typically they are a bit more simpler, let's say.
One comment about this. Nikolai is in the NL4SI project doing the thesis with Alberto, and he was working with Bayesian network, but also things related to decision trees. We were also doing some things related. I was looking at the paper for Implode. I'm not sure if the data set that you use is available somewhere or not, but maybe this afternoon or tomorrow we can go together in deeper detail about how this was implemented. Because the logic is, as far as he explained and how it's in the paper, is just you have many decision trees, you extract rules, then you have a way to look if the rules are compatible, incompatible, consistent, inconsistent. You merge, and then you have a smaller set of rules that you can show to a human. But as far as I understood, then you stop there because you give the rules, and then the interpretation of the rules is done by the manager, let's say. We were doing things to try to see if we can verbalize something around the rules that were generated. So there could be other additional layers of explainability on top of that, that is something that we may explore outside, just in case someone else has some additional question.
I must say one thing, that is, when we start this work, we were not thinking on explainability. That the idea was simply to make it affordable for the different decision makers in the university.
Yeah, but the last question is, what may you give some examples of what kind of insights could the potential rector get from visually inspecting the obtained decision tree, like the course is taught not properly or whatever else?
No, he can understand that, for instance, there are some number of courses that the level of unsuccess is quite big and can be connected with the let's say the economic power of the student, for instance. There are things that, based on the data you use as predictive attributes, that can give you a kind of profile of what is happening. And if you create, for instance, for the university, 8 different decision trees, for instance, you can have, typically what you will have is different decision trees, quite different, because they cluster according to how similar they are. Okay.
Just to put into context, João was working quite a lot in ensemble learning, but usually this type of techniques, you merge different trees with a focus on accuracy. You have some metrics to optimize the performance of your system. Here, the focus was more closer in how to improve interpretability, but one discussion that we many times have is that interpretability is not only a small number of rules, but the question is very important the domain, the specific domain, to understand the meaning of the different variables that are involved. And this is related to what Nikolai said, what is the target, what you are looking for, because this can help that maybe there could be some features that could be more relevant for one person or other, depending on the type of decision that you have to do. But again, this is something that maybe we can explore later. I don't know if someone else has any type of comment. Alberto, Nikolai, Alberto.
Just a very short question, also in this context, because I was interested on what data are you using. You mentioned now that maybe socioeconomic or markings of the students or failure success. So as far as I understood, there's nothing involved, for example, in the curricular units. You have the teaching outcomes, you have the description of the course, you have lots of natural language texts. This is nothing involved at all. So you're using data related with markings and so on. And for example, it's also involved data related with the virtual platform they use, because in some applications, in this context, depending on the time that each student spends on a specific activity or so on, there could some information related to how difficult it is, or something that could relate it with the final success or failure. Do you use information from the platforms?
We have done work also that was not connected, was done by this student but not connected with his PhD directly. That was to be able to predict success and unsuccess based on a large number of different attributes. I should say it following: this data set in particular, then we have extended this approach for other data sets. When we started with the data set of the university, we were able to do that because the PhD student his profession is to be the informatics of the university. And he has that ability. Nowadays with the NDP will be more difficult, okay? But it was a changing time, and things were possible on the time it was done. Nowadays I'm not sure.
Even could be more difficult nowadays, because with the AI Act, learning and everything related with teaching is also high-risk domain, so probably there should be more caution on what data use, which purpose, and so on. Thanks.
More questions? One thing related to the time series that you refer with LSTM, all these graphs that you saw, they were numerical things, nothing related, for example, because these recurrent neural models are used a lot in the context of transformer, large language models, or this type of things. I don't know if you have some experience trying to go in that type of series.
Yes, we are.
Because there are also people here interested in this part of language modeling that maybe
we, especially for transformers, we started to think on how we could apply this approach also for transformers, but it's a work that is not yet done. Yes, this is, let's say, a very initial work, and we believe I would like to have 3, 4, 5 students, PhD students working on this, because I think it is a very large research line that can be exploited.
Any comment or question or thing related to the talk? Because otherwise we can stop the seminar here, and then, as I say, we can talk later if someone else has interest. João is here till tomorrow afternoon, so we will see. Maybe Nikolai, we can talk in order to find a time slot that could be good for us to discuss deeper on that. So thanks everyone for coming. Thanks João again for the talk.